So thanks to the organisers, Arvin in particular, for inviting me to talk, and it's great to go forth in this session to be able to lean on the sentiments that Ari, Jack and Ricardo have already mentioned. In particular, some of the most important sentiments they mentioned that are relevant for this talk was Ari was referring to the importance of validation, and arguably it's substantially more challenging than the computational verification problem. That there's been multiple studies in the California region that have looked at sort of a handful of events. Ricardo mentioned the largest study in California that I'm aware of, looking at 30 past events. So you'll see, for comparison, the number of events that we're sort of looking at in a New Zealand context. And then both Jack and also Ricardo really highlighted the multitude of different metrics that we can use for the purpose of trying to understand simulations. And depending on whether we want to use those to validate the models or to gain further insight will depend on which metrics are the most important. So sort of the framework in which I often think about this problem is depicted on this slide, where on the left-hand portion we have the ingredients that go into producing ground motion simulations, so details about the source, path and side effects, and then some broadband simulation methodology that takes those as input, performs the wave propagation problem either in 3 dimensions or in a sort of simplified 1-dimensional context for so-called high frequency methods. On the right-hand side, then applies those ground motion simulations for future earthquakes, either individual scenarios or many scenarios multiplied by their likelihood to get probabilistic seismic hazard analysis. And ultimately, we want to make use of those in design and in engineering context. And so then validation really sits at the boundary between those two as the key method by which we develop confidence in the predictive capability of these results. Clearly, one of the challenges is that prediction is inherently an extrapolation, and so we can only validate based on observational data that we have, but that is the best thing that we can do to build confidence in that extrapolation resulting in prediction. I'm going to focus in particular on one aspect of validation, what I consider is the more robust aspect, where we're explicitly comparing against ground motions from historic earthquakes. But again, as I alluded to at the start, there is merit in other types of comparison, for example, benchmarking against predictions from other empirical models, albeit that that's comparing one model versus another model, so it's not really a formal validation. Clearly, the way in which we consider validation, in particular the bar in which we need to overcome, is a function of how we actually want to make use of simulations. Loosely speaking, we can think of the usage as falling in 2 categories. On one hand, we can have seismic design loadings defined, for example, in the form of a response spectrum or somewhat equivalent, and we're using simulated ground motions really to fill gaps in our as recorded ground motion databases for the purpose of doing dynamic response history analysis. And then the other form would be where we use simulated ground motions directly in the hazard analysis calculations in place of empirical ground motion models in order to come up with the design ground motion intensity measures, such as those target response spectrum. Clearly, the former is relatively easy as compared to the latter, which requires significant additional details that I'll sort of allude to in this presentation. Another way to think about it furthermore is also the particular context in which we wish to perform the validation, and that really is a function of how we want to use those simulated ground motions. This is a matrix that was proposed by myself and some other colleagues in 2017. We were really talking about 2 main domains in which we think about validation. On the sort of vertical axis to the left, you can see the notion of the spatial extent considered in validation, whether we're focusing on generic regions, so we're thinking in terms of ergodic prediction of ground motion amplitudes from events of certain magnitude, distance and site conditions, all the way down to the bottom where we want to use simulated ground motions to truly develop a non-ergodic site-specific estimate of the hazard. And then in the upper portion, you can see the complexity of metrics that we use for validation, which ranges from sort of historic inquisition using qualitative waveform comparisons, which are obviously useful for insight, but not for quantitative validation prediction. Conventionally used metrics like response spectra and other intensity measures such as duration, and then all the way through to complex system response, where we use multi-degree of freedom models of buildings or other geotechnical systems as essentially a surrogate for simple intensity measures that tell us the actual expected performance in these complex systems, albeit they're clearly not as generalizable as the simple measures such as response spectrum. So what does sort of conventional validation look like for individual earthquakes? Naturally, through the sort of arc of history, simulations have been used primarily for insight, and only more recently has their predictive capability got to the point where we think of using them explicitly for prediction. Because of that, there's obviously been a large emphasis on large events. So in a New Zealand context, in the past 10 years, there's been several notable events that I'm showing here. And so our research in this field started by examining ground motion simulations in the context of these events. Hopefully it goes without saying, but one important thing to mention, of course, is that to build predictive confidence, we need to use simulations for retrospective analysis in the same way that we would use them for prospective analysis. So really things that we modify should be done so in a clear and transparent way and not tweaking individual parameters. Just the one slide in terms of the sort of methodology that I'll be showing results for in the subsequent slides. We were using Graves and Patako hybrid methodology with a 1 Hz transition frequency, various different rupture generators. And then the low frequency wave field in the 3D calculation was using a 3D velocity model with approximately 20 sedimentary basins throughout New Zealand at a 100 meter spatial grid, and then no modification for shallow nonlinear side effects. Whereas then the high frequency portion of the ground motion was using a 1D velocity model with the conventional assumptions in that sort of simplified physics-based approach, and then a VS30 based empirical site response to account for sufficient soil conditions and potentially nonlinear response. So of course, for these type of historical events, we can compare with observed waveforms that have been recorded at strong motion instruments, either in a qualitative sense to gain insight, or in a quantitative sense by looking at one or more intensity measures and trying to determine directly by residuals the prediction versus observation differences. So we might see these are very common summary plots where we're looking, and for example, several of the last 3 presenters showed plots like this, residuals, both in terms of the mean across all sites, as well as some measure of the variation in those residuals from site to site. So in terms of what inferences can we really make from those sorts of comparisons? So really the key question is how much of the misfit between observations and the prediction is due to an imperfect simulation methodology, or problems in the crustal or rupture models, or incorrect parameter values that go into those crustal or rupture models. And really the answer to that question is without multiple events and multiple recordings at the same set of sites, it's really not possible to differentiate between those different sources. And so really, although we often talk about ground motion simulation validation, it's not just validation of the ground motion simulation method itself, it's also a validation of all the constitutive models that go into that, so the crustal and rupture models, as well as the parameter values for those models and how they're determined for individual geographic regions. So in that context, it's useful now to turn our attention beyond just the several large events that capture sort of all the public interest, shall we say, and look at the small, moderate and large events where we can start to gain significantly more predictive capability. So this is an illustration of the magnitude depth distribution of the centroid moment tensor catalogue that exists in New Zealand. This catalogue was sort of started to be routinely calculated at about 2003. So there's on the order of about 20 years of events that have both relatively good source locations and magnitude characterization, as well as recorded ground motions. In terms of the data points on the plot, each black point represents an event, although the events are discretized at 0.1 magnitude units and sort of single values of depth in terms of no decimal points. So for those very shallow events, it does look like there's only relatively few, although there's many points there that plot on top of each other. So taking a look at that data set as a whole, it can be useful to sort of discretize the entire data set into different groups. And you can see that I've annotated 4 different groups here, using approximately a depth of 20 kilometers as a crude delineation for active shallow crustal versus subduction events. and then delineating also in terms of magnitude, where magnitude 5 is somewhere around the boundary, where events below that are small enough that you can either use a point source assumption, or if a finite fault is used, the details or the geometry of that finite fault is not particularly important. And then obviously above that, magnitude 5 to 7, where finite fault representation becomes important, and toward the upper end of that magnitude 7 range, where actually often we find that events are complex with multiple segments and so on as well. Not all of the events are particularly useful because, for example, particularly the small events at large distances may have relatively few recorded ground motions, and therefore we can't determine stable estimates of source-related features. And so loosely speaking, there's somewhere on the order of about 850 useful events in a New Zealand context. So in that regard, I'm going to show a few results that from studies that we've done looking at active shallow crustal events. This is just 3 slides to highlight the data sets that we've been using. For magnitude 3.5 to 5 events, we've got a little under 500 events where we've performed ground motion simulations for each of those corresponding events and compared simulated versus observed ground motions for about 5,000 ground motions recorded at 200 odd stations. For the moderate magnitude data set, obviously slightly less events, 75, leading to about 2,000 ground motions, again, at a slightly different subset, but around about 200 different stations. And then finally, 14 events in the magnitude 6 to 8 range that have event-specific finite faults that have been developed from source inversion studies. They kind of cluster, as you can imagine, into earthquake sequences. So down in the Fiordland region at the southwest of the country, there's 3 events in particular. In the Christchurch region, sort of at the center of the South Arm, there were 3 main damaging earthquakes from 2010 to 2011. At the top of the South Island, there were 2 events as part of the 2013 Cook Strait earthquake, and then of course the 2016 Kaikoura earthquake in the northern portion of the eastern South Island as well. As some people had mentioned, and Artie in particular made a good point of pointing out the importance of small events. For these large events, which happen to also generally be the more complex events, actually uncertainty in the rupture description tends to dominate the simulation uncertainty. And so although these events are the most important ones, they actually have many challenges in trying to use them for validation inferences. And so it's necessary to simulate these, but it's certainly not sufficient to only simulate these large events. For each of the ground motion simulations corresponding to the historic events, we perform the simulation and then compare observed ground motions against simulated ground motions. And because we're looking at many events over many different sites as part of that data assimilation process, we use mixed effects regression. So many of you will be familiar with that process as shown through this equation, where we really start to break out the total residual as the difference between observed and simulated, and then how that's partitioned into a bias across all events and sites, a term, the between event residual, which is a function of individual events, equivalent between site residual, and then a remaining residual left over after all those terms are removed. So we can perform that type of analysis and look at results. What we're showing here as part of the small magnitude data set for crustal events on the left-hand side is an illustration of the model prediction bias, comparing in black the empirical, a New Zealand specific empirical ground motion model, in red the standard 2010 Graves and Pataka method, and then in blue a modification of that based on our prior work where we made changes to how site response was treated at long periods, and then also how the duration of the high frequency portion of the ground motion simulation was treated at short periods as well. And so we can perform these type of comparisons. They're useful obviously in an absolute sense, but really it's as we start digging a little bit deeper that we really start to find out the overall sort of assumptions in the model. As we deal with very large data sets, sort of the quality of the data is important, and in particular recognizing that there is a large variation between some data sets that are very high quality, but other portions of the data set that are lower quality. So just one illustration of this is the result on the right-hand side of the previous figure that is for the New Zealand-wide data set, which is shown on the left here. And then the Canterbury specific data is shown on the right. And so we have about 10% lower sigma value values in terms of our misfit, just illustrating the fact that we have better constraint on the velocity model and other input parameters for that region, which comes back to sentiments that Ricardo was mentioning previously as well. We can then, with so many events, we can start to look at systematic trends. So this figure is illustrating the between event residual as a function of the event location throughout the country. This is particularly the event residual from the simulations, but of course we can do that both for the left simulation and then also from equivalent empirical models that we see on the right hand side as well, to try and understand how that between event residual is actually a function of the simulation, or whether it's more telling us something about the underlying nature of the event itself. And so then this plot at the forefront is showing that correlation in the between event term. In particular, if you focus on the blue line between the modified version of the simulation and the empirical ground motion prediction. And so what we see with those high correlations is that we're seeing very similar between event terms irrespective of what prediction method we use, and therefore it's more likely a feature of the actual event in terms of variation and stress parameter and so on. So this is sort of a way that we can start looking at the data set. These are two independent studies by Kaiser and Residual that looked at stress parameter estimates. Obviously, many of you will be aware that determination of stress parameter is a function of the methodology used, and so the direct comparison from those two studies is not really that applicable, but we looked at how that estimated stress parameter compares with our independently calculated between event residual, and you do find a relatively good correlation. It's positive, but as you can see on the bottom right panel, it's really on the order of sort of 0.3 to 0.5 correlation units at short periods where we expect it to be significant. And so that indicates that, if we want to have forward predictive models that account for regionally varying stress parameter, they're going to help our prediction, but it's certainly not close to a one-to-one correlation. In a similar fashion, we obviously have repeated observation at the same set of locations, and so we can start to look at equivalent systematic site-to-site residuals. Again, I'm showing here comparisons between simulation and empirical, and again, specifically looking at the correlation in those terms. And again, if I draw your attention to the blue line comparing the modified simulation with empirical, we can see that at short periods below the transition frequency, so in the HF portion of the hybrid simulation, we almost have a one-to-one correlation in those site terms, which is really reflective of the fact that VS30-based site response is being used for both simulations and empirical methods. Then we can start even digging further. These four figure panels are showing subsets of the overall 212 ground motion stations.
2 minutes, Brendon.
Thanks, Alvin. Where we've identified cases where the features in terms of, for example, the VS30 metrics don't seem to represent other qualitative data sets. So for example, stiff gravel sites that actually have low documented VS30 values, when we look at that data set in aggregate, we see actually they do have, as a group, systematic departures from the overall model bias. And so this is ways that we can start to dig into, are there problems with the velocity model? Are there problems with the site characterization? In that vein, rather than just use VS30-based site response, we can obviously try and couple these advanced ground motion simulations with equally advanced treatment of the near surface site conditions. We've performed those sorts of studies, looking in particular at the Canterbury region, and just in a nutshell, we identified that where site response tends to be quite prominent, you can actually get improvements by explicitly modeling the site response. But where site response is not that prominent, there's generally no difference, or in sometimes actually the 1D site response analysis can give substantially worse performance. The last thing I want to touch on very quickly is the explicit consideration of uncertainty in ground motion simulations, and really this idea that for ground motion simulations to be used in seismic hazard analysis, we need to explicitly account for that uncertainty. Simply looking at the standard deviation of residuals, such as what we're looking at in this plot, is really just telling us how much we're misfitting the observations when we have a single simulation, but it's not actually propagating uncertainty in the simulation itself. So what we really want is something that's highlighted here, for example, where we have multiple realizations of the simulation due to realizations of the parameters, for example, and then we try and ensure that that ensemble of simulation realizations has the appropriate uncertainty relative to the observation. So we've performed some initial work looking at several different parameters that are varied and getting estimates of total residual. And in a nutshell, we find that with 12 different parameters, we have an uncertainty that's about 1.5 times too small relative to the misfit in the model. There's many challenges associated with these ground motion uncertainties in terms of parametric versus modeling uncertainty and aleatory and epistemic components. And we really need a staged approach by which we start with simple cases, particularly small magnitude events where the effective uncertainties is, or the number of uncertainties that are important is not that many, and slowly progress out towards larger magnitude events and finally multi-segment events. So in summary, really just to reiterate some of the points that previous speakers mentioned, that validation is essential. It requires a systematic and comprehensive approach. In particular, validation should be performed on the same data sets that we use for development and calibration of empirical models, so that really if they are the state of practice, we need to demonstrate like for like that we're able to perform better. And then we need obviously explicit treatment of simulation uncertainties as a critical element as well. So thanks very much for your time. Thanks, Arden.
Thank you very much, Brendon.